this semester. So I'll just say thank you in general to all our past, present, and future sponsors. It's my real pleasure to introduce today's speaker, Mr. Dongwon Kim. Dongwon got his undergraduate degree from Seoul National University. Then he came here as a graduate student, started working on CT reconstruction, and then sort of transitioned to working on optimization methods and made some really nice breakthroughs in that area that he won't be talking about today. He graduated in 2014. Then he did some postdocs at Harvard, at Michigan, and at Dartmouth. And then he joined KAIST, Korean Advanced Institute of Science and Technology, as an assistant professor around 2018 or so.
Yes.
And recently he was promoted as associate professor, and he's going to be speaking today to us about min-max methods, I think. So
Yes.
with that, the floor is yours. Great to have you back.
Very great. Thanks for a nice introduction. So, and it's really good to be back here. I think it's around 10 years since I left here, and I came at the right time with the snow, right? And also when I come in the morning, I sleep, so I felt everything. So it's really good to be here and meet people who I met you before. So now I'll get started. So as Jeff told me, I worked on CT, but I mostly worked on trying to do better optimization for CT. Then at the end of the PhD and afterwards, I got more into the optimization. So I'm more optimization person than medical imaging. So, and then I got really interested in gradient descent, and I had some work on X-ray methods. But now, after I got my job, I also got interested in minimax. And somehow I found that minimax, and I heard from people that minimax doesn't work well. And now people use diffusion, right? So I feel old now, but I still wanted to fix this. So I'm going to talk about that. And basically, it's gradient method and optimum. So you guys all know about this. I'm just going to expand everything that you know in minimization to minimax. That's all. So get to the point. I just want to start with some story. So I went to the NURIPS a month ago. And as you might know, GAN received the Test Time Award. And I'm sure you all agree with this because this had a huge impact in generative model, that really good impact. So deserved it. And I'm looking at the same conference, I saw a tutorial on flow matching and invited talk on diffusion Schrodinger bridges. It's all about diffusion and flow matching. But looking at GANs, even papers was really hard to see. I saw there was one paper said, GAN is not dead or something, but they're promoting, they say it's still working well, but majority are on diffusion and also the products, in commercial products, they all use diffusion. That happened. But why? As you see, GAN had really big impact. What changed? And if I ask this, I think even undergraduate who knows about machine learning will know the answer. So min-max Ross, but I'll talk about that. I'll get to that. To get to that, for those who are not familiar with the generative model, I want to start with this one. And this is from the flow matching tutorial given in the NURIPS. So they wanted to start from how they got the history of the generative model briefly. What is generative model? Here, what they do here is, this is the most recent basic idea of GAN and diffusion. And let's say we're given a data in some distribution that which we don't know. What they do here is, let's say we have some known distribution. For here, it's Gaussian or uniform, it doesn't matter. What they do here is, let's learn some mapping from this to here so that we can have a mapping that we can generate the data, given this data. So if we can come up with the distribution that is close to the real data distribution, that's what we want. How can we do that? The straightforward way is to think about direct map, as you see before. And that's basically the idea of the GAN. You try to minimize the distribution of the generated data from here and compare with this and minimize that distance. That's it. And because minimizing that distance is difficult, they transform it in the minimax form, and that's why minimax came out. And advantage of this is efficient sampling, because if you have experience with diffusion has very inefficient sampling. That's the problem. So, but the problem was min-max loss. It was difficult. So if I meet anyone, if I ask about GAN, they all complain about the tuning thing, and it always breaks down. And graduate students has to do a lot of work to look into that. And also there's no good measure to say when it's good, right? So they have to always check the output of the data and see when it works. And if it works well, you put it in the paper, you get the paper, right? So that's how it works. So then diffusion model came out. Basically, it's not that different. It's about still learning about the distribution, but since direct map, learning that it was difficult, what they do was learn the process, continuous time process to approximate this distribution. So what you do, you use SD to go from here to this distribution. And if you can learn that, well, here your network is a support function, then that's it. But since this can be written as a minimization, so they didn't have the minimization problem, the optimization problem. That was the one difference. And this worked very well. And that's why this is used in the commercial products. So is it the end of the story? No, right? So it's slow sampling. So flow matching is known to have a faster sampling and some more simpler. And the trajectory of that continuous process is simpler. So they are more, I think I heard that they are more, flow matching is becoming more popular these days. Anyway, that's the point. So at this point, I was curious. I'm not the person who works on generative model. I'm more in optimization. I was curious. What if min-max loss wasn't that difficult? Would people will be using diffusion model, or then GAN will be okay, right? Will that be, will still diffusion will be the most popular one? I'm not sure about that, but now there's more techniques going on in diffusion because everyone's working on it. I think this still it's state of the art. So today I'm not going to compete with that. I'm interested in optimization. I was curious, what is wrong? What is difficult? What makes it so difficult? Because when we start with minimax, it looks very similar, and we think in the beginning we thought that it will work well, but there was something. That's what I'm going to talk about. So to summarize, in minimization or in machine learning, regression or classification, gradient descent works so well. Even in non-convex, people thought it will not work. They can find global solution when it's over-parameterized. Of course, there is some always tricks has to come in, but we are happy with that. When it comes to minimax, similar GDA, if you run it, it doesn't work well. Why? That was what I was very curious. And that's how that's all about what I'm going to talk about this. So when I got into this and the way to solve this was to learn from GD. That was my goal. So what does GD has? What properties of GD has that GDA doesn't have? What makes different? That's something that I'm going to talk about. Of course, I'm sure that GDA doesn't work in minimax will have a lot of factors that makes it really hard. I'm only going to focus on one thing, which is pretty straightforward. So when we talk about GD, we all know that GD converts to a local minimizer, right? We kind of know about that. And some people, we just take it for granted, or with one example it works, and you might think, do we have that statement? Which seems very straightforward, right? Do we have that in minimax? And you will see that we didn't have that. And that's what I'm going to talk about. Some sort of, we have in the stronger assumption, we did, but in more general, similar to the minimization, we didn't have that. And that's what I'm going to talk about. So to get to that, I'm going to start with reviewing about this statement. How can we guarantee that? When you think about GD, negative gradient, you think it's straightforward, but there's a technical thing that you have to be careful here, and I'm going to talk about that. So let's start with the minimization. Simple with the F. We want to minimize it. We take a gradient, negative direction, and step size. And choosing the right step size is important, right? That's what we learn. If you choose the small, it's slow, but it gets the solution. If it's large, it might diverge. That's what we know. Oh, sorry, before that, we know about this. And like introduction to machine learning, this is what we learn, how we have to be careful with the learning rate, right? Okay. Actually, and it was 1D, and it was convex, but actually it was known that finding a local minimizer is NP hard in the worst case. That's actually in theory, in the worst case, it's NP hard. So saying that we can find a local minimizer, in theory, you have to be careful. But of course, we don't work on the worst case, right? We usually don't really see the worst case, but in math people, we care about, or if you want to have good theory, we want to really have the algorithm to work even in the worst case, but not everyone is worried about that because practitioners, we can apply it and then see how it works. So even in non-convex deep learning, actually, I think it's before 2010, I think when SVM was more prominent, people were worried about non-convex, right? Because there's no theory. But then practitioners used GD, but then they were able to find global solution. And it worked well. So that changed everything, I think. So after that, people wanted to understand this GD. Why does this work even for the non-convex case? And I'm going to focus on that. In optimization class, if you take optimization class, if you learn GD, if you learn about convergence rate, what you learn is GD converges to the stationary points. If it's non-convex, if it's convex, stationary point is the global solution. Don't worry. But if it's non-convex, what we usually can show is that it converges to the stationary point. Are we okay with this? If you look at this carefully, stationary point includes local minimum, but also local maximum and local saddle points. So local saddle points might be a problem. And if you think about loss function with the neural network, there may be some saddle points. It depends, but so can we guarantee that this GD converges to the local minimum? That's what I'm going to talk about. It's not my work. It's the work that I've been using here. So I'm going to talk about that. So to talk about local minimizer, and I'm going to start with this very elementary condition for the local minimizer. We know that we find the gradient because that's a first order necessary condition. And there's a second order necessary condition where Hessian at that point is positive and definite. And there's a sufficient condition, positive definite. There are three conditions that we learn. That's very basic. So as I said before, that finding local minimizer is NP hard, but in practice, what people found there is that usually the saddle is strict. There's no non-strict saddle, many examples. What I mean by that here is, if it's saddle, the Hessian of a saddle point has at least one strictly negative eigenvalue. Of course, I haven't checked all the loss functions, but in many loss functions, people found that there is a negative convergence in saddle. So why is it that important? So for GD, we don't have any hope to escape this. Or if it has a negative curvature, GD, there's a hope to escape it. That's why we have this property. So recalling that we cannot find local minimizer, it's NP hard. My goal is not to find local minimizer at this point. Our modest goal is to show that GD converges to a second order stationary point where X satisfies the second order necessary condition. Why this is a good goal? Because if I assume it's strictly saddle, what does this mean? This point is exactly the local minimum. That's the point here. So if I show this and assume this, then under this condition, we can say that GD converges to the local minimizer. And that's what we have in theory. So now, why not just focus on local minimum point that satisfies the second order sufficient condition? Have you thought this carefully? necessary condition? So I said this here, but should I only focus on the local minimum that's only satisfies sufficient condition? Necessary condition, I said strict saddle, but it might not have that, right? But is it really important? Can I just say GD, make a method, come up with a method that only converges to the point that is only has satisfied only sufficient condition? Then I don't have to worry about strict saddle, right? Would that be a better choice? Yeah. Yeah.
But we don't have.
Yeah, right, yes. But here my point is, there are points that doesn't satisfy sufficient condition, but satisfy necessary condition. Yeah, but you're right too. So here, there are many ways to motivate that, but I'm interested in machine learning. In overparameterized setting, global minima are not isolated. They're all connected. It means the Hessian is not invertible. It means it doesn't satisfy sufficient condition, necessary condition. So the success of grid GD in minimization in deep learning, if the method only converts to the point in sufficient condition, this might have not worked well. So having a method that I'm going to talk about here, I'm going to talk about theory behind this. But if this was sufficient condition only, then this might have not worked well. So I wanted to point that sufficient and necessary condition difference might be a big thing. Okay, so now I'm going to talk about a tool, dynamical system analysis, that I'm going to use extensively in this talk. So I'm going to review this for GD, and it's not that complicated. It's very elementary. You might have seen this before. I'm going to get to that. So what is that? GD exponentially converges to points that satisfy the second order sufficient condition of local minimum. I'm going to explain that. And the one that what I'm going to more focus on here is that GD almost surely converges to points that satisfy the second order necessary condition of local minimum with a random initialization. And that's actually the main focus. But talking about these two will help you better understand this analysis. I'm going to talk about this step by step. So let's review what is dynamical system. So dynamical system is xk plus w. Xk is the number of iteration. At each iteration, there's a w, and we get to the next thing. But now it's the same thing, but we're just bringing it as a dynamic system. So more of a control theory. Whether this is stable or not, I'm going to talk about that. When it's stable, it corresponds to the local convergence. What I mean by this. So given dynamic system, an equivalent point x star, which corresponds to the stationary point of our the problem, is exponentially stable if the spectrum of the Jacobian of W at that point is smaller than 1. That's known, and it corresponds to the local convergence. It's not that complicated, so I'll go on explain what that is. It means stable if for each epsilon there is a delta such that for all k, this is satisfied. So for each epsilon, there is, if you start from some radius, it always will be within some neighborhood inside. That's a stable. It's not unstable, right? And asymptotic stable means this xk will go to 0 star when it's nearby that. It's local convergence, right? And what is exponential stable? The radius is exponential. That's it. But it's all local statement. Why is it so important? Because it helps us understand GD. So we can view GD as a dynamical system. Xk minus eta gradient of fxk. You can see this W, and the Jacobian of W is identity minus eta Hessian. And if you view this as a dynamical system, GD is exponentially stable at a stationary point x star if and only if the spectral radius of Jacobian is smaller than 1. But by looking at this, a little bit complicated, but let's plug this in here. And then it's equivalent to say that the eigenvalues of the Hessian lie in the interior of the following point. And that's not that complicated, so you will be easily able to do that. So what do we have this? Then if we assume that f is twice differentiable and Hessian is upper bounded like this, and we choose step size from 0 to 2 over L. We can say that GD is exponentially stable at a point satisfying the second order sufficient condition of local minimum. You follow this? Because sufficient condition means the Hessian is positive. Eigenvalues of the Hessian is positive, right? Then it will be on the real axis, it will be, so this is real axis and imaging axis. This part will be on, if it satisfies sufficient condition, it will, all the eigenvalues will lie inside here. So it will be exponentially stable. So this is how we can relate gradient method to the condition of the local minimum. And we can say that it's G3. What we have done was to show the first step. How about the second one? Because I said there are cases where necessary condition is important. There's another paper which which inspired my work. It's by Lee, Schmidt, Jordan, and Ray. Court 2016. It's the title says everything. Gradient descent only covers the minimizers, and this is what they proved. By the stable manifold theorem that I'm not going to go in details, what they show here is that with this condition, the same as before, with the eta smaller than the previous step size, what they show here is that for any strict saddle point that we want to escape, if GD satisfies this, probability of the limit of xk being that strict saddle is 0. Here, the assumption what we need here is that there must exist a limit. So if it doesn't have a limit, then it doesn't work. But usually GD will converge to some point, so it can apply it. So in other words, if GD converges to a point, then it is almost surely not a strict saddle point. That gives us the second part here. But why? So I said that I'm not going to go over this in details, but by looking at this, I can explain a little bit. You can see that there's a negative curvature and positive curvature. If you put a point on this straight line, if I take a gradient descent, you only get to this point. But if you're at least slightly perturbed from this line, you have a effect of this negative curvature. You have some negative direction, so eventually we will get to this. So with the random initialization, this line has measure 0, so will not lie on that. It is likely to escape it. But the rate is not good, so there are people who have improved this to make this rate faster. So in worst case, it will take exponential time to escape this when there's exponentially many set of points. But anyway, this is the main idea that people have shown that we can escape strict, GD can escape strict saddle. What is interesting here is that we don't use Hessian explicitly, but it has implicit information of the Hessian, so GD can, interestingly, get to the local minimum. That is the point. So that's what I've shown. In short, GD almost surely converges to a point satisfying the second order necessary condition with the random initialization. And as I said before, with the strict saddle property, this paper claimed that GD only converges to local minimizers, almost surely with the random initialization. That's basically it, to support the theory that GD can find the solution. So after looking at minimax, I found that this comparative was missing here. And that's what I thought that I should have done, I should do. And I was able to have some progress, and that's what I want to share today. So that will be in section 4. So in other section, I'm going to also have to review the existing works. In section 4, what I'm going to talk about is, actually there was no necessary condition for a proper local minimax optima. So I'm going to first define derive the very reasonable necessary condition. I'll get to that. And show that existing GD fails to converge to points satisfying this necessary condition. If you believe that the point that satisfies necessary condition is important, this is not we want, right? We wanted to improve it. So we improve this. We modify GDA, but I don't use any second order information. I'm still using GD gradient methods, just changing a little bit, no other thing, because I don't want the method to be too complicated, because using the practitioners, and always simple is the best, right? But if it's too simple, we don't have that property. I'm going to show that with some minimal modification, we can have this result. That's what I'm going to talk about. Before we get to that, I'm going to talk about GDA and local minimax optimum, and talk about in section 3, existing results on exponential convergence of GDA to the points satisfying sufficient condition. This was known, but not for the necessary condition. And that's where I have a contribution here. So let's move to section 2. So now minimax, which is the main focus here. I want to minimize function over x and maximize over y. And very standard method for this is natural gradient method to use is to compute the gradient and take negative direction for x and ascent direction in terms of y, and we hold minus plus. That's it. Seems pretty similar to very natural, and you can think this to work well. But somehow it fails. And that's would be one reason why it's really hard to optimize minimax. And to make it simple, I'm going to introduce f, which is saddle gradient operator. I have minus to deal with this minus here. And I'm going to let Z2 concatenate x and y to make this simple. So now I'm going to use this f. And can you see where I'm heading? So not yet, sorry. So later I'm going to talk about view this as a dynamic system. And then you will see some difference because of this minus. The Jacobian of this will not be symmetric, and we have a eigenvalue and imaginary eigenvalues. Anyway, so when we have this minimax, what is the natural optimum points? I should never show the next slide, but what is the solution that we look for in minimax? In minimization is very straightforward. We want to find the point that has the minimum value, right? What is it in minimax? Well, saddle point, right? Nash, that's what all would use, right? What is saddle point? Given this, for any x, this is larger. For any y, this is smaller than, this is a saddle point, and that's what we want. That's in game theory, it's called Nash equivalent. And if you see GAN, they all want to find Nash. So there's nothing wrong. But, oh no, not yet. So local saddle. So we have saddle point, global saddle, but it's non-convex, non-concave because we use neural network. We have to have some definition in local definition. That's local saddle point, and it can be also viewed as a local Nash equivalent. And we know things well about this. The necessary condition for this is gradient being 0. Second necessary is Hessian on x and Hessian on y being positive semi-definite and negative definite. Negative semi-definite. The sufficient condition being positive definite and negative definite. This is known. Let's see whether GDA has the property that we have seen for GD. So let's view this as a dynamic system as before. Then GDA is exponentially stable at G star if and only if the spectral radius of the Jacobian is smaller than 1, which corresponds to saying that eigenvalues of DF lie in the interior of this. Is it good?
So you're using the same step size for both the X and Y components.
Yes, for now. I'm going to change a little bit, but yeah.
I mean, because physically, if X and Y have different units, you have to have a different step size, even for unit balance. So
Oh, yes. For that, yes. For now, I'm just going to assume that F is smooth with L entire F. So, but yes, for that case, you have to tune it. But for now, let's say there's no scale issue. So then can we say that GDA converges to local Nash? Where did this paper have discussed about this? Which is called the limit points of the gradient descending minimax optimization in UAPS 2018. I told you it's very similar to GDA, right? But there's slight difference, right? So what is a dash sufficient condition or necessary condition? Is the Hessian of the x and y. What does it mean? We for the points that matters, the argument that matters is only this one and this one, not the entire one. Because the coupling comes in, it changes the argument. So what it means is that they don't match. So we cannot claim that GDA comes to localness. What this shows is basically this. It can also converge to non-Nash. It doesn't, this condition and sufficient condition doesn't match because we're looking at different Hessian. So it's not possible. So there are papers who modify gradient method so that the spectrum becomes the same, but that includes Hessian information, so that's not preferable. Okay, so you have seen that GDA from dynamic system perspective. This doesn't only converge to local Nash. Then you can see that will be a problem, and why gradient students have problem. And sometimes it works, sometimes it doesn't work, because we don't have a good understanding about what solution we're looking for. And moreover, there's another paper saying local Nash may not even exist, even in the GAN problem. And there's a paper, the title says everything. Two GANs always have Nash equivalent, but there are very simple example that Nash equivalent doesn't exist. So there's also a problem. And there's another problem. Is Nash a proper optimality that we should be only looking for? So in general, if F is non-convex, non-concave, the order matters, right? If it's convex, concave, you can change the order, but here not. There's something about order. And if you look at the GAN, what it does is we minimize this distance between the original distribution, data distribution and generate distribution. And if you change the order, it doesn't make sense, right? There's order. So in that perspective, we can enlarge the equivalent point that we're interested in. So here, what it does, this is coming from the game theory. And for X, compared to Nash equivalent, for here, Y star is here, but for X, for different X, always they see Y that is, so X always see the maximized function, not the Y. Always X, because it's our outer variable. Because of the order, what we say here is that we are viewing X is always seeing the maximized problem or primal problem. And if you think about this, that doesn't seem wrong, right? And it includes Nash. So I'm not saying let's not think about Nash. What happened to, okay, it's okay. Nash. This is a little bit enlarged set. But what I'm trying to say that this is enlarged, but makes sense. But it's okay. If we were able to come up with a GDA that converts to the local Nash, then it will be fine. But there's no gradient method that can do that. And since there is a good optimal definition that we can work on, now here, one might question, are there a gradient method that only converts to this solution, right? I'm not the one who started to talk about that. Jean Netropoli and Michael Jordan in this paper, what is local optimality in non-convex, non-concave minimax optimization in ICMA 2020? They talked about this, and they call this local minimax point. And in game theoretic perspective, it's local Steigenberg equivalent. They come up with, they start with this. They say from this, they motivate to consider this equivalent and come up with a local version of that. Interesting, there was local version of the Steigenberg equivalent in 1950, and they showed that it wasn't really a local definition. Why? Because here, the only difference, if you think about local definition of the optimality, usually we just say it works for the neighborhood. That works. But here, there's a difference. If you say that, if it works for, if it satisfies this for some neighborhood, but there are examples where if you choose a smaller neighborhood, it might not work because of this max part. So what they added here is for any delta that is smaller than delta 0. So we have to explicitly say this is local. From that neighborhood to smaller neighborhood. So that was slight change, modification that made this to be a really local definition. So that's what they defined. And the next step is to come up with a necessary and sufficient condition, right? So necessary condition is this. How about that second order necessary condition? This Hessian being negative semi-definite. And here, if this is negative definite, sure complement of df is positive semi-definite. This was their necessary condition. How about the sufficient condition? Same sure complement is positive definite, and this part is negative definite. So you see that this was incomplete, right? Because this part, where is this? If I don't want this, then this is only thing, which is very loose necessary condition. If I make my method to converge to those points, then it will have non-optimal points, right? So what I will do is I will make it more stronger. And this paper called this to be strict local minimax point, and they only show exponential conversions to points that satisfy this. That was the main thing in this paper. And I thought we should expand this by dealing with the necessary condition. And that's what I'm going to talk about soon. So, but before that, how did they show that GDA converges to the strict local minimax point? Because we already have experience that GDA does not, we cannot say anything about convergence to the local Nash in GDA, right? How can they say something about strict local minimax? Actually, GDA itself cannot do that. But what they show here is that with the different step size, they can show it converges, exponentially converges to the strict local minimax point. But still, non-strict thing, they didn't discuss anything because it was more difficult. They don't have necessary condition. So let's get to this part, section 3, which is, again, the paper by, the work by this one. I'll get to that. So what is, when I say it's different step size, it means I have tau here. It's 2 times scale. You make tau large, that means I put smaller step size on this. And actually, this is one of widely used choice in practice. If I ask people who works on GAN, if you have heard about TTUR, 2 times scale update rule, I don't know if anyone has heard about. No, yeah. These days, no one uses GAN. No kidding. There are people, but they know more about diffusion. But in GAN, people found that TTUR, this kind of thing, works better. But in that paper, they only show that it converts to the local Nash. So it doesn't really match with this result. But let's see. So to make it simple, I'm going to introduce this diagonal matrix that just puts different weights. How can we show that it converts to the strict local minimax? So now, again, I changed a little bit, and that's a dynamic system. How GDA is exponentially stable if and only if the eigenvalues of this, where there's a scale, is lie in the interior of this. How can we show that? So now, if this is invertible, we can show this. How? Can anyone guess? What happens when I increase tau with the spectrum? That's a question here. What happens if tau is infinity? So yes, and what about this? So let's say here, still it's very small, but it's updated. But if I look at this, it gets close to 0, right? If it's really 0, then what happens? This part is 0. This becomes lower triangular matrix where this is 0, right? Gets 0. And what we know in spectrum is spectrum of lower triangular is same as eigenvalues of this and this block, right? So how can we show that? So this paper showed that if this is invertible, the eigenvalues of this, when tau goes to infinity or epsilon goes to 0, we have this characteristic. One here is that this UG is the eigenvalues of the this one. So you can see that previous analysis at tau goes infinity, the one part would get close to the spectrum, right? Another part will get to 0, right? But from 0, do we have information from that? It turns out that this part is the eigenvalues of S, which appeared in the sufficient condition. But here it gets to 0. But what you see here is that lambda z minus epsilon mu z, this is small o epsilon. So what you can see here is that if you see here, this one, if this is positive, it will get close to this as you increase tau. And also for this one, it gets to 0. But if this is positive, it will be getting to this way because of how you see here, epsilon and small o epsilon. So if this was positive, everything will be coming from here to 0. It was negative to 0. So this, as we increase tau, we have some information of the Hessian that is related to this sufficient condition. So because of that, what we can able to show here is that tau GEA with sufficiently large tau, we can have exponential stability at a strict local minimax point. That was what they have shown. So again, let's get back to the question I had before. In minimization, is it sufficient to have a method that only converts to sufficient condition? What about necessary condition? And that was the main question that I had. In GAN or in machine learning, we now have a lot of things, everything we overparameter and it works well. But in GAN, somehow, usually to do well, we somehow overparameterize. Then there must be a non-strict local minimax optima. But if our method only converts to strict local minimax optima and it escapes non-strict, then we're never going to have a good thing like minimization, right? So I thought I should have a complete theory here and say that some methods, we have to come up with a method that only converts to the points that satisfy the necessary condition. But the problem that I had was even necessary condition was too loose, right? I had nothing to do here. If I just say converts to this point that satisfies this, then there's nothing much. And if I assume this, then already, if I assume then this part is not the one that I'm interested in, right? So that's where I was at. So now I'm going to move on to my part. And I think I have around 5 or 10 minutes, is it?
Yeah.
Yeah, so I'll try to go fast here.
10 minutes is fine.
Yeah, okay. So now things will be, you will see something new. So before I move on, I have to introduce this, but don't I think this really carefully. But so basically, I will explain this soon, but we define something called restricted short complement. This is generalized short complement with the pseudo inverse. I have U coming in here. So it's when this is invertible, this is exactly the short complement, but now it's generalized, but not just generalized. We have some subspace that it restricts. So that's why we call it restricted short complement. But you might think, why am I find this? But I didn't find. You'll see that this just comes out from the necessary condition. I'll get to that. So what is this? By similarity transform, we may assume that this is diagonal, right? And there's zeros. That's what I'm interested in because I want this to be non-invertible. Then there will be a part that corresponds to this eigenvalues, the 0 eigenvalues. I'm going to let that part to be gamma, and U be a matrix whose columns form an orthonormal basis of transpose of range of the gamma. So you don't have to be know about details. So what does this mean? So this being positive semi-definite means this is non-negative for some subspace restricted to U here. Or if I work on the original before the similarity transform, when this V is in the range of the Hessian of the Y, F in terms of Y, that corresponds to this. Why do I care about this? Because we have our local minimax point satisfied this, and if H delta. So previously, we weren't able to find the necessary condition from here. They allowed H delta to be actually arbitrary, that goes to 0 for any delta that goes to 0. They weren't able to show it, but and even they only cared about strong sufficient condition, right? So now what we did was, I think this is not that restriction. We let H delta to be linear. I don't think that's very, or to be more precise, to be small delta, but making that linear works. So I think it's not that restrictive, but with that, so now what we're doing is we are restricted a little bit of the local minimax point, but then we were able to show that this is the necessary condition. And interestingly, independently, these authors defined similar definition and called this to be calm local optimal point. So anyway, now we have a necessary condition. Now we can talk about dynamic system. Before we get to that, now we need to talk about eigenvalue asymptotics here. It becomes more complicated. And as you see here, so there's lambda tau and df. And I want to remove this, but we weren't able to do it. But if this is invertible, that's the previous work. If we only assume that this is invertible, but this not invertible, I think this is new. And for that case, we have this asymptotics, which looks complicated, but basically, let's parse it each. So this one is the same as before. This part now corresponds to the restrictive shear complement. Now we have a dummy part here, which corresponds to the singular values of the gamma, which doesn't, if you think about the sufficient condition or necessary condition, it doesn't have any relation. It's just dummy. It makes the method unstable. That's why we see instability in minimax. So we had to deal with that. But real problem here is that this is really tricky. The tangent direction is imaginary axis. It's outside this region. That's what made it very difficult for us. So as you see here, that type 1 can be outside. Even though it doesn't matter, it doesn't matter with the sufficient necessary condition. It just can be outside this. It just can make the method unstable. So what I can say here is that tau j, even if you choose tau to be large, it can be non-strict. It can be unstable. So that's what I claimed before. And existing GDA cannot converge to those methods, probably even for non-strict local minimax points. So how can I solve this? Can anyone think of how I can solve this? Anyone? There are two types that you can think of. You don't need the details. Two ways. Anyone? So I'm just asking, not the details. Just looking at this. What should I do? Just look at this. What should I do?
Perturb something.
Perturb. Perturb means, yeah, perturb. So two things. You can make this larger to make this inside. One thing, or you can move this, right? So that's what you can think of. But drawing it's easy. And when I was thinking about this, I wasn't even now I better know about this. But at that point, I did drawing, but I didn't have a better understanding. So I was curious, what should I do? So back then, actually in minimax, extra gradient method is widely used because it converges in convex concave case, unlike GDA, because it diverges. GDA even diverges binomial problem. So EG is widely known. And if you look in EG, sorry, for those who haven't seen EG, is you do gradient update once, but you again compute the gradient at that point and update from the original ZK. That's the only difference. But why does it make a big difference? Because GG is exponentially stable at point if eigenvalues of the Jacobian is inside this thing. It's peanut shaped. And one might say, can we use, if you know proximate point, you might ask, why not? If you can use proximate point is outside this circle. So you can use proximate point, but it's computationally not expensive, but you can also think about that. So for some lambda, I can make it inside. So that's it, but I say some. Why? This can be still outside. So that's what really made it tricky here. So what we were able to say in the paper was, if that become really complicated, but the student actually did a lot of work. This part, you have to check the curvature of this because both has the same tangent. In imaginary axis is a tangent. So previously everything was tangent is here, so we don't have to worry about this one and the curvature of that. But now we have to worry about the curvature. That really made the difference. So when this curvature is this inside, it works. If not, there was no way to do that. And you might say, can we make this larger? But there's, we have only proximate point. You can think of something here, but other part, but still that's also have this tangent to this imagery axis. That's also a limit. There's a limit. So we cannot do further. There's always a limit. There exists something that makes us difficult here. So that was it. And that was about exponential stability, right? But as I said before, actually, I'm more interested in almost sure convergence, right? That was about some non-strict, but I'm more interested in almost surely converge to a second order straight point, but previous work wasn't that one. So now I need this. Then what I need to do here is I need some definition that's analogous to the strict saddle point. And we say this to be strict non-minimax point, where at least this one and this has at least one strictly negative curvature. That's similar to strict saddle point. And we again applied stable manifold theorem, can show that probability of the limit of ZK is strict non-minimax point is 0. So we have similar results with the specific step size choice. So in other words, tau EG converges to a point, then it is almost surely not a strict non-minimax point. But of course, I said before that there's something that is still a problem, right? I was very not happy with that. So I thought this is impossible to solve. Then I got to this here. So I have only a few slides. I think I can finish this soon. So then I said, let's enlarge this. But I said there's a limitation. We cannot do better. Then another one was move this here. Actually, it took me more than a year to figure this out because I thought there's no way because I only thought about extra gradient or proximate point. But how can I perturb it? Can anyone think of how we can perturb that towards inside here? No, if you just perturb it, then you're changing the problem. That's not what I'm asking. I want the problem where we want the station point, optimal point to be the same, only implicit regularization, not the explicit regularization. Explicit regularization, I can easily move it. Yeah, implicit. And now you can see that. Yeah, for me, it took more than a year. So anyone can answer, then you're smarter than me. Yeah.
Partial scaling you talked about in the previous section.
Yeah.
Does that
No, it's only
affect those?
no, as tau increases, it only gets to this. There's a curvature that doesn't make it. Yeah, I cannot move that. Yeah.
See some sharpness result?
Huh?
Some sharpness type result to
What's-
get
What's
Weak sharpness.
Well, I don't know what that is, sorry. So now I'm saying don't use any complicated thing. Just say I still want to use gradient method.
Can you so in the method you described, you updated X and Y simultaneously. What happens if you alternate them?
So she's my committee member. She's smarter than me, right? she was my committee member. Yeah, yeah, yeah. If I yeah, she's faster than me. Yeah. So okay, so that's what I'm trying to do. Implicit regularization. So I knew about alternative method, but alternative method usually in theory there are no benefits. It's like there are methods that people in GAN they use alternative method, but in theory, you see all papers, simultaneous and alternating doesn't have a big difference in theory. If you apply into bilinear problem, simultaneous method diverges, alternating method just circles around. That was difference, but in convergence wise, there was no difference. So I never thought that carefully. But then at some point that came back and I thought, oh, I should try that. So this part actually corresponds related to this section. And I thought we need to put regularization. If I put regularization on this side, why? Then it can easily solve it, but implicit. So this is how I did it. So simple alternating update doesn't work. I have to be careful with the scaling. So I introduced this alternating update where I compute Y after the update here. And there's gamma here, which will control that. So when gamma is 1, this is simple alternating method that you mentioned, but I have gamma, which needs to be tuned. So if I choose gamma to be square with tau, why I have to be careful? Because I don't want to affect other two types, only the first one. If I affect the other two, then I'm messing up. I have to fix the other two, but only that one. So I have to be very careful with the scaling. If I choose gamma to be square root tau, why? Because you see that it has square root epsilon. So there's a reason why I have that. If I choose that like this, then everything will move here. So now I'm happy. And I hope you guys are happy too. And this is it. This is the method that we have. So, it's a little bit complicated, but I always wanted to make it as simple as possible. This was the one that we had. And it's alternating and EG, but 2 time scale in a different scale. And if you are familiar with the PDHE, primal dual hybrid gradient method, or Chambon-Poch, actually, this part corresponds to that. When I wrote it, I didn't realize that because I was rushing to submit the paper. But later, if you think about this, it's about primal dual update. You have a momentum, right? And that corresponds to this different scaling. So with there's a similar type recipe here. So, but with the EG, then we can claim that that our method almost surely converts to the local minimax optima. But for that case, while tau GDA almost surely escapes. So now we have a theory that can converge to the solution that satisfies the necessary condition. So to sum up, we come up with the more complete necessary condition, and we show that existing tau GDA fails to converge to the point that satisfies such necessary condition. We now have a method that converges to such local minimax optima, and that's it. And actually, my open question, I said, yeah, I don't care much about GAN, but yes, I do. With this, I'm hoping that I can improve GAN. So I'm just interested in how can we improve generative model. Can gradient method be powerful as GD is really good at regression and classification? It does really well, right? It finds us global solution and it generalizes well, but it doesn't work well. So can we have the same thing in minimax or GAN? That's my open question. Thanks for listening. Thank you.
So I'm curious, the structure constraint, which allows you to.
Yes.
If you have a convex constraint, that would lead you to some sort of differential inclusion, right? Because the right-hand side would be, whatever, x dot is equal to the negative of the projection on something, right?
Which part?
So I'm just saying in general.
Yes, it will change, yeah.
Yeah, so the right-hand side becomes.
What's the right hand, sorry? The
right-hand side
projection?
of that dynamical system.
Yes, yes.
So I'm curious if there is work on gradient descent or even unlikely on gradient descent.
Yes, good question, yeah.
Convergence for strain.
Yes, if you look in a constraint case, projected gradient descent, then you cannot have this result. So there is a paper saying if you do for minimization projected gradient, you cannot say it almost surely converges to the local solution. There is a probability that where reason that converges to the saddle point. Yeah, so strict saddle. So projection makes it difficult. So directly extending this to projection is difficult. So for me, I show this GAN to be, I show the one that has a constraint, but original GAN it doesn't have a constraint, so you can work on that. For constraint, it's even for gradient descent, we don't have that result. So
So have you taken your new algorithm and tried to train it again with it?
yes, I have done it in a very simple one.
And
So we don't have I have a global solution. So this always have to go with saying the method globally converges to stationary point. And with this local convergence, we can say that it globally converges to the local minimizer or something. And we have that, but with under some conditions. So I ran with a very small number and actually we were able to find a global solution for that simple one. So I'm positive that this will get better, but not yet. Yeah.
Is that minimax max mini that is affect results?
Yes. If you go back here. Yes. If it's non-convex, non-concave, switching it matters a lot, like this case. It's switching means totally different thing. Yes. Always, this is the distance, right? Generator, minimize the distance, make this distance too small, because this is difficult to solve. We get to the minimax, and max is the one that computes the distance. So if you switch it, it has no meaning here. Yeah. And other GAN, it's just, this is for Washington distance, but other GAN is all, the original one is JS GAN within JS divergence. And also if you switch it, there's no meaning there. So always there's an order.
Also, based on necessary conditions, can you use those conditions to derive some algorithm from that?
From that, so you mean you want to use Hessian information to better converge to that points, or?
Like, maybe it's to challenge it to have some Hessian information.
Sorry. Get it.
I mean, like think of like first order, second order method.
Secondary method then. So I haven't thought about secondary method. There exists secondary method, but to my best of knowledge, there's only method that assumes Hessian is invertible. Usually Newton is invertibility, right? So, and I haven't seen any paper from starting with this necessary condition yet. So I'm trying to advertise this. If you want to think about second order, yes, I think that's also interesting. Yeah.
last little question. So the small GAN that you tried, was it using ReLUs? You have a lot of second derivatives in your analysis,
Sorry.
right? And even standard neural networks are not really even first order differentiable if you use a ReLU, right?
My student ran it, but yeah, I think he used Marilyn, but I'm not sure. Yeah, it's neural network, very small, like one hidden layer. Yeah.
Okay.
Yeah.
Just curious how much it matters. Like if you come up with an algorithm that has reasonable theory, but then in fact the actual network is not twice. the
Yes,
size.
that's what I'm trying to figure out.
Yeah, okay.
Making work in a more general setting. Yeah. Well, of course, still the setting that I'm going to consider will be far from the practice, but try to get close to that. Yeah.
Well, let's thank Dongwon again. He will be here tomorrow in the morning and several of you are meeting him, but if you wanted a chance to talk to him, we could certainly arrange that. So thank you again, John.
Thanks very much. Yeah. And hopefully we can connect again.
I was just gonna say, nice to meet you, Dave. Thanks for staying. Thanks for coming.
Yeah, I'll send you an email. Maybe we can talk at some point.
Yeah.